Kia ora and welcome to video 21 in the series Agile Algebra. This video, you're stuck with me. Unlucky, I guess. Here is the question. It's quite quirky. We've got a quartic equation. We need to find the values of c, that coefficient in front of x cubed, and so that we can get a line intersecting it at 4 different points. On the surface, I guess it looks like a discriminant question because we're talking about the number of solutions involved. However, I don't use the discriminant in my solution to the very last line of working. So you need to conceptualize it, think about what's actually happening here before you jump into your solution. Maybe use Desmos, and then, as always, pause the video, give it a go before you look at the solution. Okay, to start, we need to conceptualize this. We need to work out what the heck's going on. We've got a quartic equation, and we want this quartic equation to intersect a line. It says so there is a straight line. It doesn't specify what type, what gradient, what y-intercept or anything. But we want a line that intersects this quartic at 4 different places. So the first thing to realize is that quartics don't all look the same. If I just graph y equals x to the 4, for example, it's a pretty boring curve. It almost looks like a parabola. It's terrible. It's got to go for the origin. It almost looks like a parabola. It's just got a flatter turning point through the origin there. So we'll explore what different quartics look like, and that helps us get a better understanding of the problem. I'll use Desmos. I've already prepared this earlier, and you can see there that that's for a particular value of c, we've got a quartic there that's got 3 turning points and 2 points of inflection. The points of inflection are between the turning points. And so with this, I can find a line there that cuts through the quartic in 4 different places. But if I change c, c 3.7 there, this quartic here doesn't have 3 turning points, and it doesn't have 2 points of inflection. And if we cycle through to negative c values, the quartic, see how it changes from that one in there has 3 turning points, so we'd be able to find a line. We'll just adjust the gradient, there we go. But if we slightly alter, there's a turning point here. I didn't mean a stationary point, but where it changes. Okay, so that one there it's got a minimum at this point. It's got a couple of points of inflection in there, I think, but it doesn't seem to have any other stationary points. At least that I can't tell without zooming in. So, with that in mind, we're actually given a problem that looks like a discriminant question, because we're wanting to find 4 points of intersection, but it's a quartic, so we're actually going to use differentiation. The first attempt at solving this problem without thinking about it conceptually, I tried doing this. Okay, I said, oh, there's the quartic, equate it to a line. If you rearrange it into a standard form, this equation here has different scenarios depending on what c is. It could have 4 real solutions. It could have 3 real solutions, where one of them is repeated. Okay, a quartic always has 4 solutions to it, but 3 distinct and then 1 that's repeated. It could have 2 real, and then the other, they could be both repeated, or the other 2 could be complex conjugates. So if you know about complex numbers here, you'll know that an equation that's got real coefficients, which this one does, this quartic has real coefficients, if there are complex numbers that solve the problem, for example 1 plus 5i, then 1 minus 5i, the conjugate, would have to also be conjugate pairs. You could have 1 real, and it could be repeated 4 times. could have one real repeated twice, and then a conjugate pair. And by the way, I'm loosely saying complex numbers here because real numbers are technically complex numbers with an imaginary part of 0. Loosely speaking, complex numbers, NCA refers to them as numbers like a real part and an imaginary part, but you could also have no real, and it's 2 conjugate pairs. So there's so many different scenarios here, and I just wanted to go straight into discriminant, but of course the discriminant only works for a quadratic equation. So we can differentiate the polynomial, the original quartic, not the rearranged polynomial. So if we find the derivative there, using our NCA level 2 differentiation skills, and at this point we want this to have 3 solutions. Okay, if it has 3 solutions to it, it's going to have 3 stationary points, and therefore we're going to be able to find a line that cuts it. But I guess the problem with that is, like it will definitely have a real solution. Cubics have to have a real solution if they've got real coefficients. It's not possible to draw a cubic that doesn't. Even the boring basic x cubed looks like that. So we could, factorize this and then look at the discriminant on the remaining thing. And I tried that, but it was really, really messy. So we're going to consider the points of inflection instead. So differentiate again. And it's important to realize at this point that when we solve this equal to 0, we are trying to find points of inflection, but our x values that we get aren't necessarily points of inflection. Okay, they're possible ones. So the second derivative here equals to 0. We want it to have 2 solutions because that will give us the potential for 2 points of inflection. Just on a side note, if I had y equals x to the 4, the quartic equation that I started off with up here, if I differentiate this once, I get 4x cubed. If I differentiate it again, I get 12x squared. If I differentiate it a third time, I get 24x. Now, solving the second derivative equal to 0, it has one solution, x equals 0. And you think, oh, maybe that's a point of inflection. But then when you substitute it into the third derivative, you also get 0. And in fact, this concavity, the second derivative gives us concavity. It's always positive, except at 0. So there is no change in concavity. And when we look back at the curve there, again, this is assuming that you know a little bit about concavity here. It's concave up on both sides of the origin. No change in concavity means it's not a point of inflection. So here, we want our second derivative to have 2 solutions. They aren't necessarily going to be points of inflection though. So we'll use the discriminant on that. Discriminant b squared minus 4ac, inverted commas around that because we're using c in the problem as well. And we want that to be greater than 0. And if you do a little bit of tidying up there, you end up with c squared is greater than 32. So c is bigger than root 32, or c is less than minus root 32. Now, just a last pointer on, are they points of inflection? So if we have a c value in those ranges, do we get 2 points of inflection? Or do we just get 2 points where the second derivative is 0? So if we look at this second derivative, it's a parabola, and we are solving it greater than 0, so we're finding out 2 points where the second derivative equals 0. So it's a positive parabola. It might look something like this. Y dash dash on that axis, x on that axis, and these are our points where the y dash dash is 0. They have to be points of inflection. in this case, because we're going from positive concavity to negative concavity to positive concavity, there are changes in concavity. Whereas for this particular graph, when y dash dash was equal to 12x squared, well, of course that looks like this, and positive concavity on both sides, and so not a point of inflection. Okay, so that's the answer to the problem. C is greater than 32, or C is less than minus root 32. I think I missed the square root on that the first time I said it. And if we just check that on here, put in square root 32 as one of the boundary points, we can see there that there are no stationary points. But then if I don't know, just add a small number to it, like 1, it doesn't look like we've achieved it unless we zoom out. Oh, that's enough. That's enough for there to be two inflection points, because I can just turn the line around and boom, we're cutting it at 4 different positions. Okay, so that seems to be working, and then we could also try the negative C values to test. Hopefully you found that video useful. It's quite nice to see that sometimes an algebra problem can be solved using calculus knowledge and vice versa. Catch you in the next video.